So, hello everyone, I'm Yuxuan from Huazhong University of Science and Technology. Today, I'm going to introduce our work, LOFT, a log-free and adaptive learning index with high scalability for dynamic workloads. We first start with the dynamic workloads. We define such workloads that contain indoor operation as dynamic one. In dynamic workloads, the data size will engross and the newly inserted items has high possibility to change the data distribution. And such workloads are widely exist in real-world applications, for example, Facebook's, and some of them are even write-heavy. To achieve high performance, we prefer to maintain the data within the memory systems because it plays a critical role in the computer system. It lies between the cache memory layer and the storage layer. It bridges the performance gap between the high-speed CPUs and the low-speed storage systems. To efficient management the data within the memory systems, we usually use index, for example, the B+ tree or the hash maps. However, there exists a dilemma between the data growth speed and the slowdown of DRAM scaling technology. The left figure shows that the size of stored data showing a rapid growth in the data volume over the years. However, in the right figure, we can see that the rate of decline in memory prices has slowed down. Therefore, we need a space-efficient index to save memory while it can scale to large volume of data. We first look at the traditional index structures. For example, we look at the B+ tree. We take B+ tree as an example. We can see the index of operation in B+ tree relies on the point-chasing operations. As we all know, the point-chasing operations are time-consuming. And also, we need to store a lot of linear nodes and pointers, so it will occupy a large amount of memory. When the data size increases, the little tree will grow to a larger one, so the performance will be decreased because the tree gets higher, we need to go through a longer path. So this does not look good. Let me introduce you the learning index. The learning index uses the models for predicting the position of the keys. It uses the model-based calculation, so it's very fast than the traditional index structures. Also, it only needs to store the models instead of a lot of linear node or pointers. With learning index, it's space efficient and also high performance. This seems a good choice for scaling the index for large volume data. So we wondered, is the learning index the optimal solution? We then evaluate the performance of existing learning index in dynamic workloads. The left figure shows the performance in read-only and read-most workloads with 24 threads. We can see when we just slightly increase the insertion operations, just 5%, the average performance of existing learning indexes decreased about 50% by average, and for leap, it even dropped by 70%. So we can say that existing learning index failed to scale to dynamic workloads. We also found that they failed to simultaneously achieve high throughput and high scalability. The right figure shows their performance in read-intensive workloads. We can see when we talk about the throughput, we think LXPlex is a very perfect choice because it shows much higher throughput. However, it can only scale to 24 threads. In contrast, although X-index and FANDEX show much lower throughput, but it can scale to 48 threads, or much higher scalability. For learning index, we want them to achieve the following goals in dynamic workloads. The first one is that we want them to be space efficient. Luckily, learning index can achieve that by only store a small number of parameters. And we also want them to have efficient query performance. And luckily, the learning index can achieve that by using the model-based calculation. However, we found that existing learning schemes are failed to achieve high performance in dynamic workloads because it cannot simultaneously achieve high throughput and high scalability. We found that it's not trivial to design efficient and effective learning index in dynamic workloads due to the three challenges. The first one is the interference introduced by insertions. This shows a simple example. If we want to insert a new items into the learning index, we will first use the models to get the position. And we will find that, there is no empty slot. So how to handle the insertion? There are two design choices. The first one named in-place insertion. This means that we preserve some free slot in advance, so we can insert the data into their predicted position. In such a way, it will have good query performance because we can use existing models to obtain the newly inserted one. However, we need to lock the entire data node as the LX+2 because we need to shift data for sorting, so we need to lock the entire data node. It uses the coarse-grained locks and lead to poor scalability, so this is bad. Another design choice is that we can use auto-place insertion. This means that we keep the data in the data array immutable and accommodate the newly inserted items into an extra buffer. For example, the X-index takes such designs. It will have good scalability because the data are separately stored and we can take a highly scalable structure as the buffer. However, it will have poor query performance because we need to check both places. So we found that existing scheme interfere with concurrent or subsequent reads. The second challenge is the collision between the indexing and retraining. When inserting a bunch of records into the NER index, the data distribution will change, so we need to relearn the data distribution for performance improvement. There are two design choices. The first is the blocking retraining schemes as LX+ does. It performs retraining in an actively way. It means that when a front thread performs the index operation, it will check whether the condition is met. If the condition is met, it will actively trigger the retraining. So this can process the retraining in a very timely way. However, it will incur non-tail latency because the retraining is in the critical path. Another design choice is that we can use the background thread to periodically check the data node as X-index does. The advantage of such design is that it removes the retraining from the critical path. However, if in the write intensity workloads, the retraining task can be very heavy. With limited number of background threads, we may fail to handle the retraining task in an in-time way. So the question is how to achieve in-time and lightweight retraining. The last challenge is the mismatch between the fixed parameters and diverse access patterns. Existing designs, it uses a static triggering mechanism. It triggers retraining once the condition is met, and it uses static parameters for retraining. So let's think of a simple example. In the write intensity workloads, can we just trigger the retraining in advance to prevent the sharp performance degradation in the future? Can we just preserve more free slot in advance to reduce the retraining frequency? So we propose our solution named LOFT. To address the challenge one, we propose an error-bounded insertion scheme, and to solve the challenge two, we propose log-free retraining. And for the third challenge, we design a self-tuning retraining schemes. We first introduced the error-bounded insertion scheme. For insertion, LOFT leverages the model for prediction, and then it will get a position for the get a position, and then it will get a predicted range for insert the key. In LOFT, the index operation will continuously cast the empty slot within the predicted range. We do not shift for the sorting. Instead, we just use the cast to occupy an empty slot within the predicted range. If it fails, it will check whether the key is equal to the inserted one to avoid duplicate keys. So in such a way, concurrent insertions can be handled concurrently without using any locks. But there can be a situation that a thread wants to insert items into the data array, and you will find that, oh, there's no empty slot within the predicted range. In LOFT, we propose an expanded learning bucket. The expanded learning bucket is just like a small data array, but with different models. We just expand the model in the data node to accommodate the insertions. So in such a way, the index operations within the expanded learned bucket just performs like they in the data array. And the concurrent insert operations are executed in a log-free manner. By leveraging the error-bounded insertion, it enables all index operations to be executed in a lock-free manner. In LOFT, we decrease the read performance because we do not sorting the data, but we can minimize the operate interference. For read, we cannot just directly use the binary search. Instead, we need to linear search. However, in LOFT, the predicted range is small, so the overhead is reasonable. And notice that to guarantee the correctness of operations, we leverage the soft delete. The soft delete means that we maintain the key in the data array, but instead we just invalidate the value. The retraining process in LOFT can be divided into 3 stages. In the copy stage, the background thread will set the retraining flag to be true and then initialize the append-only log. And then it will copy the data into the new data array. The modification during this stage will be recorded into the append-only log. But we exploit the highest 2 bit in the value to avoid redundant logging during the retraining process. During the retraining stage, the background thread will start retraining and obtain the new data nodes. If the worker thread wants to update the K1, it does not need to log it into the append-only log because we already record the K1 in the log. So we can use the pointers in the append-only log to obtain the latest version of the value. And in the sync stage, and when we enter into the sync stage, the new data nodes become invisible to the worker thread, and the retrained data node becomes to the shadow one. The index operation can just operate upon the new data nodes. For example, if we want to update the K5, we just operate that in the new data node. But we will label them as the latest one, so the following read can identify that the value in the new data node is the latest one. And the background thread will sync the record from the tail of the log to synchronize the modifications. In LOFT, we introduced a self-tuning retraining scheme. For the write-intensive workloads, we will increase the expansion factor of the data node, and we will increase the predicted range so that the retraining frequency can be decreased. And for the code data node, we will decrease the expansion factor, and we will increase the prediction range to save the memory space for storing the index. And in the read-intensive workloads, we will decrease the predicted range to decrease the search length. There are other design details about LOFT you can find in our paper. For evaluation, we compare LOFT with convention index structures like mass-tree and LRT, and we also compare it with a set of learned schemes. You can see the blue ones. We first evaluate the scalability in the read-intensive and the write-intensive workload. We can see here, due to using the in-place insertion designs, the Alex Plus, Sally, and LOFT each achieves higher throughput in the read-intensive workloads. And we can see, due to our log-free design, LOFT achieves the best scalability. In the read-intensive workload, it can achieve to 18 threads, and in the write-intensive workloads, it can achieve to 48 threads. And also combine all the designs together, the LOFT improves the throughput by 1.7 times to 14 times on average. We also evaluate the adaptiveness of the indexes. We change the workloads every 400 million operations by adding 20% in those operations. We can see the average throughput of all indexes decline as the proportion of the insertion increases because the insert operation has longer latency than the read. And using our log-free retraining schemes, it enables LOFT to avoid such severe performance jitter like Alex Plus. And the LOFT illustrates the long-term stability thanks to the self-tuning retraining mechanisms. In summary, we found that existing learned indexes show limited scalability in dynamic workloads because they will display sharp performance degradation in the dynamic workloads and fail to simultaneously achieve high throughput and high scalability. So we propose LOFT, a log-free and scalable learning index. We propose error-bounded insertion scheme, log-free index operations, and retraining process, and the self-tuning retraining mechanism. By using all these designs, LOFT significantly improves the throughput with high scalability compared with the state-of-the-art schemes. And thank you, that's all. I'm open to any questions or comments.